Hola, chaps. Let's learn. Hola, chaps. Mr. Turek here. I found a PowerPoint labeled Stoichiometry Review, Mass to Moles to Molecules, and I've decided I'm going to work through this PowerPoint with you as a review exercise for you and a lead in for the limiting reactant, excess reactant type calculations that you're mastering this week. So here we go. The first slide comes up and asks, please convert 333 grams of aluminum hydroxide to moles. So to do that, there's a little conversion table set up, and you're to fill it in. You can pause this video at any time and fill it in yourself, and then I'm going to reveal the answer as we go streaming through this. So I need to figure out how many moles there are in one. I need to figure out how many grams there are in 1 mole of aluminum hydroxide. So I go to the handy dandy periodic table, which you should have and consult, because I don't really expect you to be able to read it here where I'm working on this, right? You can just see a little bit of my screen. So for aluminum, and I'm going to round this off because it's close enough for me to just do this almost in my head type thing. For aluminum, I see it's almost 27 grams per mole for aluminum. And then for oxygen, it's 15.999. Let's just call that 16. For hydrogen, it's 1.008. Let's call that 1. 16 plus 1 is 17. So each hydroxide is 17 atomic mass units. I have 3 groupings of those hydroxide atoms. That's what it means to have the subscript 3 outside the parentheses surrounding the OH. So on my calculator, if I go 27 plus 3 times 17, it works out to a total of 78 grams per mole. And what I would really like to encourage you to do is to have a mental expectation before you turn on your calculator of what kind of answers you would expect to get from this. So as I look at 333 grams and I compare that to 78 grams for 1 mole of this stuff, I can say to myself, wow, 333 is more than 4 times bigger than 78. I mean, rounded off, 78 is about 80. 4 times 8 is 32. So 330 is more than 4 times greater than 78. So I'm expecting in my head an answer that's going to work out to be greater than 4 grams per 4 moles of this stuff. So let's click on it. There you can see they also chose to round it off to 78 grams, and you've got the conversion table. Everything in the numerator means you multiply, everything in the denominator means you divide, and you choose to set it up so that the units will cancel as you work through this. So the number of grams in the first column cancels the number of grams in the denominator of the second column. And now the units will be converted from grams to moles. And the result was, as we expect, a bit more than 4 moles of this stuff, 4.27 moles according to the calculator. There's a whole bunch of these on this PowerPoint. So I'm just going to kind of quickly guide you through them and tweak it up a little bit as we go along, give you a limiting reactant, excess reactant type problem as well. This next one says convert 0.212 moles of potassium nitrate to grams. Well, I need to figure out how many grams there are in 1 mole of potassium nitrate. And that's the first blank on the conversion table here. The second will be to figure out, well, really, I guess that's all there's going to be. Let's see how it goes. So for potassium nitrate, KNO3, I go to the periodic table and I say potassium is about 39, nitrogen is about 14, each oxygen is 16, but I have 3 of those oxygens, 8, 16, 20. So I have 48 atomic mass units amongst those three oxygens. And so I add these things up. Oh, 1, 2. And I'm getting approximately 101 grams per mole for the potassium nitrate. So if I have 0.212 moles, that's like 1/5 of a mole. 1/5 of 100 is about 20 grams. So I'm thinking this is going to be a little over 21 grams of this stuff. All right. So the conversion is the first column is what we start with, 0.212 moles of potassium nitrate. The second column is the conversion. Everything in the numerator is multiply, everything in the denominator is divide, and you set it up so that the units will cancel. In this case, we're canceling the units of moles. So moles in the first column cancels moles in the denominator of the second column, and you've converted this into grams with a result that we expect to be a little over 21 grams, works out to 21.4 grams of potassium nitrate. All right, you are becoming masters of chemistry. Here's another one. Convert 7.5 times 10 to the 22nd power molecules of carbon tetrafluoride to moles. All right, so the first column will be what we start off with in the numerator, 7.5 times 10 to the 22nd power molecules. The second column will be the conversion between molecules and moles. Now, this problem doesn't need the periodic table at all, because they're converting from a number of molecules to the number of moles of those molecules. And a mole is just like a dozen, a huge number representing how many of those quantities do we have. So what you need for this one is Avogadro's number. You've probably memorized it, and of course you have it in your reference sheets. Avogadro's number, represented as Na, is 6.022 times 10 to the 23rd power. And it doesn't matter what we're talking about. This planet has about 10 moles of kilograms of mass in its core, underneath its surface. So it could be anything. It could be ping pong balls. It can be molecules. It can be shoelaces. So this one is ratioing what they gave us, 7.5 times 10 to the 22nd power, to Avogadro's number, and that will turn it into moles. In this situation, I see that the number is smaller than Avogadro's number, almost by a factor of 10. So I would expect the number of moles to be a bit more than 1/10 of a mole. Plugging it into your calculator, and sure enough, it's 1/8 of a mole. All right. And you could have figured that out approximately by saying, well, 60 divided by 75, 60 divided by 15, 75 divided by 15, and worked out that the ratio is, 1/8. All right. Next one. Convert 212 grams of sodium bromide to molecules. All right, so in this situation, yes, we're going to need to know how many grams of sodium bromide there are in 1 mole. We can't go directly from grams to molecules. We have to go from grams to moles, and then from moles to molecules. So I pull up the periodic table and I ask myself, how many grams are there in 1 mole of sodium bromide? And the periodic table says sodium is about 23 grams and bromine is about 80 grams. And so I have about 103 grams per mole. Now, no doubt you're asking, hey, Mr. Turk, can I just round off like that on homework? No, you students get to pull out a calculator and be a little bit more precise than I'm being right now. I'm just doing this quickly because otherwise this is going to be a very, very long video instead of just a long video. All right, so approximately 103 grams per 1 mole, and I see I've got more than double that in terms of my initial grams. So in my mind, I'm doing the ratio already and saying, hey, 212 out of 103, that means I have 2 moles. It means actually a bit more than 2 moles of sodium bromine. And then for every mole, I have Avogadro's number of molecules. So if Avogadro's number for 1 mole is 6 times 10 to the 23rd, then Avogadro numbers for 2 moles would be 12 times 10 to the 23rd power, or 1.2 times 10 to the 24th power. So my estimate is going to be a little bit more than that number of molecules. Here's the conversions. 212 times 1 Avogadro's number per the number of grams in 1 mole of sodium bromide. So again, they also chose to round it off to 103 grams per mole. Notice that it's set up so that the grams in the denominator of the first column cancel the grams in the, I'm sorry, I said denominator. It's set up so that the number of grams in the numerator of the first column cancel the number of grams in the denominator of the second column. And instead of writing mole on top of the 103 grams, they just directly converted it from moles to molecules per mole. And the results, sure enough, a bit over 2 moles, which works out to a little over twice of 6.022 times 10 to the 23rd power. That's 12.4 times 10 to the 23rd power, or in scientific notation, 1.24 times 10 to the 24th power. All right, here's another one. Convert 1.39 times 10 to the 24th power molecules of water to grams. Well, so the first column will be what we start off with, 1.39 times 10 to the 24th power of molecules. Next column will be how many moles are there in that number of molecules. And really, I would add a third column that says how many grams are there in that number of moles. For the grams per moles, you can do that in your head. Call oxygen 16 grams, call each hydrogen 1. 1 plus 1 plus 16 means 18 grams per mole. All right? For the 1.39 times 10 to the 24th molecules, you look at that and say, well, I know that Avogadro's number is 6 times 10 to the 23rd power. This is 13.9 times 10 to the 23rd power. So it's more than 2 moles, a little bit over 2 moles. And if 1 mole is 18 grams, then 2 moles would be a little over 36 grams. So I'm expecting this to come in somewhere close to 40 grams per mole in the end. And here's what they filled in. The given went in the denominator of the first column. Then, instead of writing how many moles that is, and then how many grams there are per mole, they combined that both into the second column and said, divide that by Avogadro's number, and the result is how many moles you have. Multiply that by the number of grams of water per mole of water, and you'll end up with the total number of grams. And the result is a bit over 40 grams, 41.6 grams of water, starting with 1.39 times 10 to the 24th power molecules of water. Another one. Now we have a chemical reaction. And as I glance at this, I see it's a balanced chemical reaction, not just a skeleton. Therefore, all the molecules seem to be correctly written. Sodium is a +1, chlorine is -1, so sodium chloride, that's correct. Fluorine is diatomic, so it's written with a subscript 2. Fluorine is diatomic, so it has a subscript 2. So the equation as the skeleton was written correctly. The coefficients are balanced because I see 2 sodiums on the left, 2 on the right, 2 chlorines on the left, 2 chlorines on the right, 2 fluorines on the left, 2 fluorines on the right, all well. And the question is, how many grams of chlorine gas are made from 145 grams of sodium chloride? So what's implied in this question is that I have an excess amount of fluorine gas. They didn't use the term, but if they are telling you I'm starting with 145 grams of this first reactant, and they mention nothing about the second reactant, you are to assume that the first reactant is the limiting reactant, and the one that they didn't tell you about is excess. We have unlimited quantity of fluorine gas Don't worry about how much of it there is. So this conversion, you can see the table is set up with multiple conversions. We have to go always through the balanced chemical reaction. We can't just say, oh, if I start with 145 grams of this, then I'm going to end up with 145 grams of that. Instead, we always have to go through how many moles of the stuff we're talking about. 2 moles of sodium chloride to start off with. And for every 2 moles of those, we only produce 1 mole of chlorine gas at the very end. We don't actually care about the fluorine or the sodium fluoride in this particular question. They're saying start with the sodium chloride, don't worry about fluorine, it must be excess. Don't worry about the sodium fluoride, just tell me how many grams of chlorine gas do we end up with in the product. So we're going to start off with figuring out how many grams there are in 1 mole of sodium chloride. And that's something where we can go to the periodic table as before and say, all right, sodium chloride. Let's see. Sodium is approximately 23. Chlorine is 35 and a half. So I end up with 58.5 grams per mole for sodium chloride. I didn't feel comfortable rounding chlorine to a whole number in this case because it's so close to being half an atomic mass unit. So I'm just going to leave it there like that, 58.5 grams per mole. Now, if I'm starting with 145 and 58 is what it takes to be 1 mole, I can see immediately that I'm starting off with more than 1 mole. If I double this, well, that's still not as much as 145. So I'm starting off with more than 2 moles of sodium chloride. If I triple this, that's greater than 145. So between 2 and 3 moles of sodium chloride is what I'm starting off with. Now, for every 2 moles of sodium chloride, I only make 1 mole of chlorine gas. I've got a bit more than 2 moles here, so I'm going to end up making a bit more than 1 mole of chlorine gas. 1 chlorine is 35 and a half, so 2 chlorines would be 71 grams. So in my head, I'm already expecting that I'm going to have an answer that's a pinch more than 71 grams of chlorine gas is my answer. Now, if I end up with something that's way different from that, then I need to be careful and go back and check and ask myself, well, did I divide when I was supposed to multiply? What did I do that is different from what I expected it to be? And I expect you to do this reasoning before you rely on your calculator so much. Okay, don't just blindly trust your calculator, because if you punch in the wrong number and you don't know that it's a wrong number, well, that's sad. Okay, you want to have an expectation and always challenge yourself with the answer before the calculator does it for you. So, in this situation, I'm expecting that kind of an answer, and I'm going to do a follow up question for this as well. So, in this particular one, here's what they're saying: 58.45 grams of sodium chloride per mole. That's the second column. Sure enough, that was the 58.5 grams that I was approximating. So you're converting, the first column is what we start with, 145 grams of sodium chloride. Everything in the denominator is divided, that's the bottom. Everything in the numerator on top is multiplied. We always set it up so that the units will cancel as we go from column to column to column. The first column begins with grams on top. So the second column has the grams on the bottom, and we're converting from grams of sodium chloride, table salt, to moles of sodium chloride. The third column is the ratio based on the balanced chemical reaction written in red at the top of the screen. It says for every 2 moles of sodium chloride, I only make 1 mole of chlorine gas. So the ratio is 1 mole of chlorine for every 2 moles of sodium chloride. The chlorine goes on top, the sodium chloride goes on the bottom, and column 2's numerator cancels columns 3 denominator. So now we've converted the 145 grams of sodium chloride into moles of chlorine gas. The last column is taking 2 chlorine atoms which together have a combined mass of 71 grams per mole of chlorine gas. And multiplying that by the output of column 3, the moles of chlorine gas will cancel, and we end up with our answer, which we expect to be, again, a little bit more than 71 grams. And sure enough, 88.1 grams of chlorine gas matches my expectation. All right, the next topic that you're working on, the one that we're finishing up this week with, deals with limiting reactants and percent composition and theoretical yield. So I'm going to stay on this slide and give you a question that's not on the PowerPoint. So bear with me as I work through this. My question becomes, what if I were to start with 145 grams of each of those two reactants? Now, as you look at this, I would classify this as a single displacement reaction. I have two reactants, two products. The sodium changes partners from being hooked up with chlorine to instead being hooked up with fluorine. The fluorine at first doesn't have anyone. It exchanges its position with chlorine, so the chlorine ends up by itself. As an exercise in limiting a reactant, my new question for you is, what if I were to start with exactly 145 grams of both sodium chloride and 145 grams of fluorine gas? Well, approximately, in fact, we can use the numbers that's already on the screen. For every 145 grams of sodium chloride, I should rephrase that. For every 58.45 grams of sodium chloride, I have 1 mole of sodium chloride. So if I ratio 145 by 58.45, which you can't see on my screen unless I were to do more work for you than I feel like doing. Can't do it. It's out of focus. Too bright. It says 2.48. Okay, so here's my claim. I was given 2.48 moles of sodium chloride in this particular chemistry problem. Now, what if I started off with also 145 grams of fluorine gas? How many moles would that be? Well, off to the periodic table. One fluorine atom is 18.998, and I'm going to be more precise this time. So I'm going to go 145 divided by, open parentheses, 2 times 18.998, close parentheses. So what I'm doing is in my calculator, very rapidly, is I'm saying I need to know how many grams there are in 1 mole of fluorine gas. Fluorine gas is 18.998. I need 2 of those, and I'm starting off with 145 grams. So 145 grams of fluorine gas times whatever 2 times 18.998 is, and that will tell me how many moles I have. So kind of in one fell swoop, this works out to be 3.82 moles of fluorine gas. So my question for you is, given that I'm telling you I'm starting off with equal quantities in terms of grams of sodium chloride and fluorine gas, and now having done the calculation that shows that means I'm actually starting off with 2.48 moles of sodium chloride and 3.82 moles of fluorine gas, my question becomes, which one of these is a limiting reactant? Okay, so look at the equation and puzzle it out for yourself. I'm starting off with a little bit more than 2 moles of sodium chlorine. And for every 2 moles of sodium chlorine, I need 1 mole of fluorine gas. In reality, I am approaching 4 moles of fluorine gas. So which one do I have plenty of, and which one is a limiting reactant? Pause if you need to think. The answer is that the sodium chloride is a limiting reactant. I'm going to run out of that. I have way, way more fluorine gas than I need for this particular problem. So this is the excess reactant. So the calculation for this particular problem doesn't change if I told you that I only gave you 145 grams of fluorine gas at the beginning of this problem to start off with, because this shows that's way more than I need anyways. I only need half of 2.48. So approximately 1.25 moles instead of the 3.82 moles of fluorine gas. So, that would be less than I can do in my head. Way less than 145 grams of fluorine gas that I was given. All right, let's move on to the next PowerPoint slide, and it looks like this. And you're scared because you see this huge conversion table, but you're becoming skilled in chemistry, so you're looking forward to doing this, pausing this, figuring it out before I work out the solution. This one goes. How many grams of oxygen gas are made from 211 grams of potassium chlorate? Well, it's a decomposition reaction. It looks correctly written as far as the skeleton goes, and it looks correctly balanced. 2 potassiums on the left, 2 on the right, 2 chlorines on the left, 2 on the right, 6 oxygens on the left, 6 oxygens on the right. So it's set up correctly, and it's decomposition, so we don't have to worry about limiting or excess reactants. Instead, we could just ask you questions about the two different products. And they're only asking about one product. So the question was, how many grams of oxygen are made from 211 grams of potassium chlorate? Step one, first column, write down what we're starting with in the numerator, 211 grams of potassium chlorate. Step two, convert those grams to moles. Step three, or column three, use the ratio of the balanced chemical equation to convert moles of potassium chlorate to moles of oxygen. We can see already that for every 2 moles of potassium chlorate, we're going to be producing 3 moles of oxygen gas. And step 4, because they're asking for the answer in grams, not moles, calculate how many grams there are in that quantity of moles of oxygen gas. All right, so going to the periodic table, and I'm just going to approximate it. Potassium is 39 atomic mass units. I have 1 chlorine, and that's 35.5, let's call it. I have 3 oxygens. 1 oxygen is 16, so 3 oxygens would be 48. And adding this together, I get 122.5 grams per mole for potassium chlorate. So approximately 211 is almost twice that amount. So I have almost, but not quite, 2 moles of potassium chlorate. Now, based on the ratio of the balanced chemical equation, I can see that for every 2 moles of potassium chlorate, I get 3 moles of oxygen gas, and therefore, if I'm starting with almost 2 moles of potassium chlorate, I must be ending up with almost 3 moles of oxygen gas. And 1 mole of oxygen gas would be 32 grams. So 3 moles would be approaching 100 grams. Let's see how it goes. There's the 122.55 grams per mole for potassium chlorate in the second column. Again, it's set up so that the grams cancel with the first column. The third column is the ratio from the balanced chemical equation that says for every 2 moles of potassium chlorate down there in the denominator, I'm going to produce 3 moles of oxygen gas written up there in the numerator. And then finally, for every oxygen molecule, I have 32 grams for every mole of oxygen molecules. So, beep, 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 we're expecting an answer close to 100, and 82.6 grams of oxygen is what we end up with. Next, a decomposition reaction. It appears to be written correctly in the skeleton form, and it appears to be balanced correctly. Just as you'd memorize that water is H2O, we expect you to memorize that ammonia is NH3. It's a molecule, it's very useful for fertilizer. The question is, how many grams of nitrogen gas are made from 60.0 grams of ammonia? You can't use the ratio for grams. You must convert the grams to moles and then use the coefficients in the balanced chemical equation to convert to moles of whatever we're looking at, and then go from those moles to the grams for that substance. So the conversion table starts off with 60 grams of ammonia in the numerator of the first column on the left of the conversion table. Then you're going to convert that to moles of ammonia. On the periodic table, it says nitrogen is 14 and hydrogen is 1. I have 3 hydrogens, so 14 plus 1 plus 1 plus 1 is 17 grams. 60 grams compared to 17 grams is more than 3 times as much. So I'm expecting that I have a little over 3 moles of ammonia to start off with. The ratio from the balanced chemical equation says for every 2 moles of ammonia, I end up making only 1 mole of nitrogen gas. So if I'm starting off with just over 3 moles of ammonia, I'm only going to be making a little over 1.5 moles of nitrogen gas by that ratio, a 1 to 2 ratio. 1 mole of product for every 2 moles of reactant. Well, 1 mole of nitrogen gas would be approximately 28 grams. So 1.5 moles would be 1.5 times 28, 35. So I'm expecting a little over 35 grams of nitrogen gas out of this. Here we go. And you can see they rounded off a little bit too. So first column, numerator, is what we start off with, 60 grams of ammonia. Second column converts from grams of ammonia to moles of ammonia. Third column, based on the balanced chemical reaction, converts from moles of ammonia to moles of nitrogen gas in the ratio of 2 moles nitrogen gas in the numerator for every 1 mole of nitrogen gas in the numerator for every 2 moles of ammonia gas in the denominator. And finally, fourth column on the right, for every 1 mole of nitrogen gas, I need 28 grams because it's 2 nitrogen atoms, not 1, in this diatomic molecule. And do the math, and it works out to 49.4 grams of nitrogen gas. Next one. I have 2 moles of magnesium. I add to that 1 mole of oxygen gas, and I produce 2 moles of magnesium oxide. And by the way, I'm using moles, but you can use the same ratio with atoms and molecules. So I have 2 atoms of magnesium. I combine that with 1 diatomic oxygen molecule, and I end up synthesizing 2 magnesium oxide molecules. How many grams of magnesium oxide are made from 3.82 moles of oxygen gas? All right, so the first column on the left, numerator, is where we fill in what we're given, 3.82 moles of oxygen gas. There's no need to calculate how many grams there are in a mole of oxygen because they don't care. They're already telling you how many moles we have to work with. So, next step is going to the balanced chemical equation written in red and answering the question, so how many moles of magnesium oxide am I expecting to end up with? Well, the ratio is 2 moles of product for every 1 mole of oxygen gas. So I'm doubling whatever I have in the first column. So if I take 3.82 moles and I double that, that's more than 7 moles of oxygen gas. Less than 8, but more than 7. 7 to 8 moles range of magnesium oxide. I said oxygen gas, magnesium oxide. So more than 7 moles of magnesium oxide. Last, looking at the periodic table, I see the magnesium is 24, oxygen is 16. I'm going to use a calculator. 24.3 plus 16 means 40.3 grams per mole. And I said I had at least 7 of that. So I'm expecting over 280 grams of this product to be made. Let's see what we have. First column, numerator, is what we were given. Second column is from the balanced chemical equation, the ratio of moles. Third column is the number of grams of magnesium oxide per mole of magnesium oxide. And you plug it into your calculator and you get 308 grams of magnesium oxide. Now, before I just click onto the next PowerPoint slide, I want to ask you, what if I turned this into a limiting reactant problem? What if I told you that I had 3.82 moles of magnesium to start off with and 3.82 moles of oxygen gas to start off with? Under that condition, which one is the limiting reactant? Okay, that was meant for you to pause and figure out the answer. So for every 1 mole of oxygen, I need twice as many moles of magnesium to make this stuff work. If I have an equal amount in terms of moles of each of the 2 reactants, then it's the magnesium that I'm going to run out of first. I'm using that up twice as fast as I'm using up the oxygen. In fact, I'm only going to use up half of my oxygen. So if I started off with 3.82 moles of magnesium and 3.82 moles of oxygen gas, I'm going to end up with 0 moles of magnesium left over. That's the limiting reactant. It's all used up. And I'm going to end up with half of 3.82 moles of oxygen gas left over. That will be the limiting reactant. That means my final answer will be reduced by a factor of 2. Instead of 308 grams of magnesium oxide, I'm only going to be able to produce half that amount, which you know in your head it would be 154 grams. All right, next one. I see this as sodium oxide and magnesium fluoride combine to produce sodium fluoride and magnesium oxide. And as I look at this, I see it is a double displacement chemical reaction. The skeleton seems to be written correctly. The coefficients seem to be written correctly. The question is, how many molecules of sodium fluoride are made from 33.8 grams of sodium oxide? Well, the conversions will be, I need to go and start with my given in the numerator of the leftmost column. So I'm going to write 33.8 grams sodium oxide in the upper left column. Next column, I'm going to convert those grams to moles. Then, next column, I'm going to use the balanced chemical equation written in red to come up with the ratio of moles of sodium fluoride to the number of moles of sodium oxide. And I see at a glance, it's a ratio of 2 to 1. For every 1 mole of reactant, I'm going to be producing 2 moles of product that I'm interested in. And I'm ignoring the magnesium fluoride, I'm ignoring the magnesium oxide. Those are not part of the question, and therefore I'm assuming that the magnesium fluoride is the excess reactant in this situation. Their final question is, how many grams of sodium oxide do I end up with? Oops, how many molecules of sodium fluoride do I end up with? So I need to, after I figure out how many moles of sodium fluoride I have, I need to multiply that by the number of molecules per mole using Avogadro's number to work out how many molecules I end up with. All right, so what would I expect in this case? For sodium, I see it's approximately 23 grams per mole. So if I double that, that would be 46 grams. Add to that the 16 for oxygen, and I have approximately 62 grams per mole for the sodium oxide. If I'm starting off with 33.8 grams, that is a pinch more than half of 62. So I'm starting off with just over 0.5 moles of sodium oxide. Based on the balanced chemical equation, I see that for every 1 mole that I start off with, I am producing 2 moles of the product that I'm interested in. So if I'm starting with just over half a mole of sodium oxide, I must be producing just over 1 mole of sodium fluoride. And then by Avogadro's number, for every 1 mole of anything, it's 6.022 times 10 to the 23rd power. So if I have a little more than 1 mole, I'm going to have a little over 6.022 times 10 to the 23rd power molecules as my answer. All right, here's the math. Again, the top left column is the given that I started off with. The second column converts those grams to moles. The third column uses the balanced chemical reaction to work out the molar ratio. And the last column says for every 1 mole of sodium fluoride, I have Avogadro numbers of molecules in it. And the result, sure enough, a little bit more than 1 mole would be a little bit more than 6.022. They get 6.56 times 10 to the 23rd power molecules sodium fluoride. All right, and now for my off-script question once again. What if I gave you 33.8 grams of each of the 2 reactants? So I gave you 33.8 grams of sodium oxide and 33.8 grams of magnesium fluoride. Calculate, please, which one is the limiting reactant in this situation? Pause, figure it out. All right, meanwhile, I'm not pausing, right? I'm just going on. So for me, I can see already, based on what's on the screen, that 33.8 grams of sodium oxide divided by 62 grams per mole means I have 0.5452 moles of sodium oxide. And I suppose you can't see what I just wrote. 0.5452 moles of sodium oxide. Now, if I start off with 33.8 grams of magnesium fluoride, then I go 33.8 divided by open parentheses, and inside the parentheses I'm going to put the total mass of 1 magnesium and 2 fluorines. So magnesium is 24.305 plus 2 times 18.998, close parentheses, enter. And my calculator says 0.54, so incredibly close to each other, 25 moles of magnesium fluoride. Wow, these two values are so close to each other that if I had just done this approximately in my head, I'd be skeptical and say, well, I better check it a little bit more carefully. So there's still a difference. They're not the same number. It says 0.5452 moles of sodium oxide, 0.5425 moles of magnesium fluoride. So again, I put the question to you, which one of these is a limiting reactant? Which one of these is the excess reactant? Okay, so looking at the balanced chemical reaction, you see that I need the amounts in a ratio of 1 to 1. For every 1 mole of sodium oxide, I need 1 mole of magnesium fluoride. So in this case, the smaller number is the one that I'm going to run out of first. 0.5425 is a little bit smaller than 0.5452. And therefore, the magnesium fluoride is the limiting reactant, and the sodium oxide is the excess reactant. Now, in this problem, as originally given, we assumed that the magnesium fluoride was excess. But in reality, the way I've changed the problem now, the magnesium fluoride is a limiting reactant, and it's about 0.003-ish moles smaller than what we started off with. And so that's a tiny change. These two are coincidentally so close to each other in terms of their masses that it's a tiny change. But still, it would modify my final answer and reduce it by that tiny amount. So my final answer, instead of being 6.56 times 10 to the 23rd molecules of sodium fluoride, would be a pinch less, 6.5 something less times 10 to the 23rd power. Let's just move on anyways. And I see we're at the end of the line. So I'm happy with that. This concludes this PowerPoint called Stoichiometry Review. And in this PowerPoint, I tried to not only have you become confident and competent in setting up a conversion table to go between grams and moles and molecules, but at the same time, it's a big lead in to what we're doing this week of identifying which one of the reactants is the limiting reactant and which one is the excess reactant. All right, this concludes this long presentation for now.